So this crystal structure, we can see at first glance it looks like, you know, it's based on some kind of hexagonal symmetry. Let's take a closer look and make sure that we understand it. So the first thing you should recognize about this is that this arrangement of atoms is a close packed arrangement in one plane, or in 2 dimensions. So this area, if these were just circles, these would be packed as closely as they possibly can. So this is a close packed plane that I'm running my hand over right now. That's a close packed plane. Now if I turn it 90 degrees, we can see along this way is a close packed plane. There's another close packed plane in a different position. And here's another close packed plane on the bottom in another position. So we can see, in fact, that if we look at these planes at 90 degrees to the planes, we can see the close packed planes are stacked in an ABA arrangement, or the positions of atoms in this top plane are actually in the same position as the ones in the bottom if you look straight down, and that's in this direction right here. So if we see close packed planes stacked up in an ABA arrangement, we know right off the bat it's HCP. Now if we just look at a close packed plane like this one right here, these are close packed atoms in 2 dimensions, and then we see another close packed plane. Again, this is a close packed arrangement, these atoms are close packed, and we position them on top of each other. Anytime we do that, we actually create interstitial sites between them, and we create 2 different types. We create octahedral, where the interstitial site is actually touching 1, 2, 3, 4, 5, 6 atoms. And we also create tetrahedral, where the interstitial site is touching 1, 2, 3, and in the back there 4. So this interstitial site right here is tetrahedral, and that's octahedral. And in fact, if you look normal to the surface of a close packed plane, that is, we look this way, if you can see right through, so this interstitial site right here, and this one, that's an octahedral interstitial site. And if you can see the plane immediately below, or see the atom immediately below, that's a tetrahedral interstitial site. And they always alternate, octahedral, tetrahedral, octahedral. Okay, this crystal structure here, at first glance, take a look at it. You can see a cubic arrangement, atoms at the corners. And if you look straight on to any one of the faces, you'll see that there's an atom right in the middle of the face. So this is, in fact, FCC, or face-centered cubic. And you can see as well, cut away, if there was another atom here and here, this little spot right here, or in fact the place where this flag is indicated, is an octahedral interstitial site. 1, 2, 3, 4, plus 1, 2 more, 6 atoms touching that. Of course, there's also an octahedral interstitial site in the very center of this structure. 1, 2, 3, 4 atoms, 5, 6. So right in the very center there is an octahedral interstitial site. And there are also tetrahedrals. If you look at 1, 2, 3, 4, between those atoms right there is a tetrahedral interstitial site. Okay, with this model we can see this, again, the stacking of close packed planes. These 6 atoms belong to a close packed plane. They're arranged in a close packed arrangement in 2 dimensions, as are the plane of atoms on the surface of the table and the one just above it, these 8 atoms right there. Now, if we stack up the 3rd layer of atoms, you'll see we actually have 2 different positions that we could put the atoms into. Either these spots right here, or we could put them into these spots right here. You can't occupy them both at the same time. The atoms don't fit into those two spots at the same time. But you can fit them in either of these. So we can form this structure here, or this structure here. Again, that's this one or this one. And with our knowledge of the stacking of close packed planes, we can actually determine which structure is which. Again, if we look perpendicular to these close packed planes, and you see that this plane here on the top and the plane on the bottom are directly over each other, that's an ABA arrangement of close packed planes, and this is HCP. Now if we move to this interstitial site right here, you can see these atoms are no longer directly over the top of the bottom ones, and this is a FCC arrangement. A, B, C positions. There's 3 different positions normal to the close packed plane. Another interesting thing you can see about FCC, this is again, I've made FCC again. If we look normal to this, excuse me, this top plane is not in the same position as the bottom. We can also see we've made a close packed plane that we can see this way, which is not parallel to this close packed plane. We've stacked up close packed planes in this direction, but we've also created a non-parallel close packed plane. Anytime you see non-parallel close packed planes, you know it cannot be HCP. In HCP, the only close packed planes are the basal planes stacked up one on top of each other. So this is FCC. So what's this funny looking structure here? To what crystal structure do these atoms belong? Well, you may be tempted at first to say, well look, there's a plane, there's another one, and this atom belongs to another plane up at the top. And it looks like it should be ABA, because this atom here resides directly over the top of this atom right here. So you may be inclined at first glance to think this is HCP. But remember, these planes are not close packed. That arrangement right there, this square arrangement, is not close packed. In fact, this is the face, the conventional face of an FCC unit cell, or one of the 100 planes. These are close packed directions, but this is not a close packed plane. So the trick to this structure is identifying the close packed plane, which is here, and here, and here, and here, realizing that you have now close packed planes that are not parallel to each other. This is FCC. It cannot be HCP, it's FCC. And in fact, these 4 non-parallel planes all belong to the 111 family of planes, and they're in fact unique 111 planes. Here's another funny little structure. We've got some planes appear to be stacked on top of each other. And at first glance, as before, you may think this is an arrangement of ABA. But we can only use that approach of stacking sequence when we're referring to close packed planes. These atoms are not part of a close packed plane. Again, they're part of the faces of the FCC unit cell, or the 100 family of planes, which is not close packed. So we can't look at the stacking of these planes to determine if it is FCC or HCP. But once we've identified that this is actually one of the 100, or faces of the unit cell, it becomes a little bit more clear that this is in fact FCC. This is one face. If we turn it this way, we're looking at a portion of the structure here, or the other face. If you imagine you remove these 2 atoms, you would have another FCC face at 90 degrees to that along the back. We've got another traditional FCC face, and here, if we removed these 2 atoms, you'd see the conventional 100 type face of this unit cell. So this structure is FCC. Another way to look at this is to realize that you've got close packed directions that are crossing each other at 90 degrees. And if you think through the structures that we've covered, FCC and HCP and BCC, in BCC the close packed directions cross across the cube diagonals, or the 111 directions, and those are not crossing at 90 degrees. In HCP, the close packed directions cross at 60 degrees. But along the face diagonals of FCC, the close packed directions do in fact cross at 90 degrees. So once you see the close packed directions crossing at 90 degrees, you're fairly certain that it's FCC. The only exception, of course, I suppose, could be simple cubic. Simple cubic would have close packed directions at 90 degrees, but it would be fairly easy to identify that if you saw the planes stacked one on top of each other. It'd be almost as if you took this midplane out and squished these two down. That would be simple cubic. If we look at this arrangement here, again, the directions are crossing at 90 degrees. The close packed directions are crossing at 90 degrees. This is one of the 100 faces of FCC. Or it could be. And in fact, if we stack the atoms up this way, it's the exact same structure as we saw with this little model in one of the other clips. So by stacking these up, we've formed an FCC structure. And I just wanted to show you what the simple cubic structure would look like if you stack these directly on top of each other. You'd see a simple cubic arrangement. Again, the close packed directions are still at 90 degrees, but it's fairly easy to identify that the structure is simple cubic. This is a tetrahedral interstitial site, so named because it forms a four-sided solid. So the solid that it actually forms looks like this little solid that I have here that's stuck to the table. But this is a four-sided solid, and then right in the very center of that is the tetrahedral interstitial site, and this is a tetrahedral solid. So here we have 6 atoms forming an octahedral site at their center. So the octahedral site has a coordination number of 6. At the center of these 6 atoms is a little space. You could fit another atom. And this is the octahedral interstitial site. It's named octahedral not because it has 8 atoms touching it, but because it forms an 8-sided solid. So I've just made that little solid right here. If you imagine a face across each of these triangles, you'd have an 8-sided solid. 1, 2, 3, 4. So 4 on this side, and then 4, just broke it, 4 on this side. So this is an octahedral interstitial site right in the center, right there where the tip of my finger is. And that's the same space that is in the center of this interstitial site.